A developer dropped the wrong table. Your backup is from midnight. The business wants 2:47 p.m. back. Midnight restore loses the whole business day. PITR is the clean path back to the exact second before the wrong table was dropped. The clean mental model is a timeline. First, take a base backup, a complete photograph of the database at one moment. After that, PostgreSQL writes WAL files, which are the film reel of every change. Then a disaster happens. PITR restores the photograph, replays the film, and stops at the recovery target, such as 2:47 p.m., before the bad command. Step 1 is to keep the WAL. PostgreSQL writes WAL all the time, but old WAL segments can be recycled after checkpoints. PITR only works if those segments are archived before they disappear. If the archive has gaps, recovery can stop before your target. That is why WAL archiving is not optional. It is the historical record that makes time travel possible. In PostgreSQL.conf, focus on 3 settings. Wall_level equals replica writes enough information for recovery. Archive_mode equals on enables the archiving pipeline. Archive_ command is the command PostgreSQL runs for each completed WAL segment. %p is the full source path. %f is just the file name. In production, replace a simple copy with a durable archive strategy. Now create the archive directory. The command is simple, but the ownership matters. PostgreSQL must be able to write archived WAL segments, and regular users should not modify them casually. For a tutorial, local storage is fine. In a real environment, this archive should survive a server loss, so use a backup host, object storage, or PG backrest. After changing WAL archiving settings, restart PostgreSQL. A reload is not enough for every related setting, so use a restart in this tutorial. Then verify the configuration from SQL. Archive_mode should return on. Archive_ command should return the command you configured. Wall_level should be replica. If this verification fails, do not continue to base backups yet. Step 2 is the base backup. Think of it as the anchor point for recovery. It is not a logical dump. It is a physical copy of the data directory, taken while PostgreSQL is running. The archive gives you changes after the backup. A more recent base backup means less WAL to replay, which means a faster recovery during an incident. Here is the current command. PG_base backup -d chooses the destination directory. -fp uses plain format, which is easy to inspect. -xs streams WAL during the backup, so PostgreSQL can make the copy consistent. -p shows progress. For larger systems, you may choose tar format, compression, and a proper retention tool. Do not trust a backup just because the command printed no error. Check the backup label. It records the starting WAL location and the start time of the backup. Then check the size so you know files were actually copied. In production, backup verification should be automated. You want alerts for failed backups, stale backups, and broken archive paths. Step 3 is the disaster drill. A recovery process you never rehearse is only a theory. We create a table, insert 1000 rows, record a safe timestamp, then deliberately drop the table. This gives us a clear pass or fail result. Either the rows come back after PITR, or our process is not ready for production. First, create test data. This table is intentionally simple. The purpose is not schema design, the purpose is proof. We insert 1000 rows so the restore result is easy to verify. Before breaking anything, always make sure the table exists and the count is what you expect. Your recovery test needs a visible success condition. Now record the safe time. This is the most important operational habit in the whole demo. Run select now and copy that value outside the database. If a risky migration starts at 250, you may choose 247 as the clean target. Without a target, the recovery team guesses. With a timestamp, PostgreSQL has exact instructions. Now we simulate the mistake. Drop table users. The table is gone, and a query against it now fails. This represents the bad migration or accidental command. Notice the difference between panic and process. Because WAL is archived and a base backup exists, this is no longer the end of the story. We have a timeline to replay. Step 4 prepares recovery. Stop PostgreSQL, move the broken data directory aside, copy the base backup into place, add the recovery settings, then create recovery.signal. That signal file tells PostgreSQL to enter recovery mode on startup. Do not delete the broken directory immediately. Keep it available until the incident is fully understood. Stop the server before moving files. Then rename the broken data directory instead of overwriting it. Copy the base backup into the expected data directory path. Finally, fix ownership recursively, because PostgreSQL must own the data directory. These file operations are simple, but they must be done carefully. One typo here can extend the outage. Now point PostgreSQL back to the WAL archive. Restore_command tells PostgreSQL how to fetch each archived WAL file it needs. Recovery_target_time is the exact stop point, here 2025-06-04 at 1447. Recovery_target_action equals promote means that when recovery reaches the target, PostgreSQL becomes a writable primary automatically. Create recovery.signal and start PostgreSQL. On startup, PostgreSQL restores the base backup state, then calls restore_command repeatedly to fetch WAL files. It replays changes until the target timestamp. When it reaches the target, it stops recovery, creates a new timeline, removes the signal file, and promotes. Watch the logs for selected new timeline ID. Now verify the recovery. The users table should exist again, and the count should be 1000. PG_is_in_recovery should return false because the server has promoted. This is the first successful recovery point, so here is the soft reminder. Subscribe if you want more practical PostgreSQL recovery and operations walkthroughs like this one. The final checklist is simple. WAL archiving must be enabled and monitored. Base backups must run on schedule. Recovery targets must be recorded during risky operations. Restores must be rehearsed quarterly, not invented during an outage. For production, use pgbackrest or a similar tool for compression, retention, encryption, parallelism, and object storage. PITR is not a backup feature. It is your last clean path back from a production mistake. That sentence matters because backups alone do not answer every incident. PITR connects a physical backup with a continuous history of changes and an exact recovery target. Set it up before you need it, test it before you trust it, and keep the checklist ready.